Okay, in this video, this doesn't directly relate to any of our topics and subtopics, but I want to talk about one of the essential skills, and I'm going to make a number of these videos up through the year, but one of the essential skills that we need to understand in dealing with physics is the concept of proportionality. This video is basically aimed to be basically an introduction into proportionality. There are maybe some things that I'll cover again in more detail in a later video. I also tend to do some videos like this that relate to, say, for example, doing evaluations of experiments and some other general sort of skills that we need to do, maybe planning an investigation, those sort of general skills that we're going to use right through the year. But this first one looks about how we use proportionality that we can derive from some of the relationships that we look at, and how we can use that to do calculations or to interpret data that we look at, either that we see in a question or data that we might obtain from doing an experiment ourselves. So let's look at using proportionality. We're going to use an example using Newton's second law. An object of mass m experiences an acceleration a of 10 meters per second due to the impact of a force F. And in the first scenario here, we want to determine the acceleration if the force was doubled. So let's firstly just look at, well, what is Newton's second law? And in this case, I like to write Newton's second law maybe slightly differently to get used to it, rather than F equals ma, because this is saying that the acceleration is proportional to the force. Acceleration is proportional to the force and inversely proportional to the mass. So what we can say based on that is that the acceleration is proportional to the force, because this question is asking us about the relationship between the acceleration and the force. So they're the two things that we're interested in. So this little symbol here basically means proportional, or proportional to. So the acceleration is proportional to the force. So if we double the force, we would get 2 times the acceleration. So even though we don't in this question know what the force is or the mass is, because we know that the relationship is proportional, if we double force, then we must double acceleration. That's what it means to say something is proportional to. So the acceleration is equal to 2 times 10, which is equal to 20 meters per second per second. Let's look at the second case here now. Determine the acceleration if the mass was doubled. I'll just rewrite out Newton's second law. And we can see now that the acceleration is proportional to 1 on the mass, because the mass is on the bottom. So what we're saying there, that's another way of saying inversely proportional. Inversely proportional to. So in this case, the acceleration is proportional to 1 on m, which is equal to 1 on 2. So the acceleration is equal to a half times what it originally was, 10. So it's equal to 5 meters per second per second. That's how we show a relationship using proportionality. In the last one, we've got a slightly more complex case. So we start with the relationship that we're using, which is where we get our proportionality from. So we know now that the acceleration is proportional to the force and inversely proportional to the mass. So, just rewriting that out, just trying to keep you probably wouldn't do quite this much working out every time, but keeping it consistent. So we know now that the mass is halved. So we've got a half on the bottom line. So that's the mass is halved and the force is doubled. So we are going to have in this case that the acceleration will be equal to 2 divided by a half, and if you do 2 divided by a half, hopefully, or you know how to do dividing by fractions, you times by the reciprocal, you will see that we get 2.5 is equal to 4, so we get 4 times the original acceleration. So the acceleration would now be 40 meters per second. So that's just looking at a simple example using proportional to and inversely proportional to, and then a combination of those two. And then we will look in the next slide about where we have a slightly more complex proportionality relationship. So let's look at an example using centripetal acceleration now. A car rounds a circular bend with a centripetal acceleration of 2 meters per second. Determine the centripetal acceleration of the speed of the car doubled. So what's the relationship we're interested in here? Well, centripetal acceleration. AC equals V squared on R. And the question is telling us about acceleration and speed or velocity. So they're, if you like, the two things that we want to pull out. So we can say the acceleration is proportional to V squared. So if we double the velocity, we need to realise the velocity is squared in that relationship, so that we will basically get 4 times the force. So the new acceleration will be equal to 4 times 2, which will be equal to 8 meters per second. Now, I won't go through, basically the other relationship we'll come up with later on in this course is looking at if we have the term on the bottom squared. But I think you should be able to use this process to work that out. Okay, let's talk about graphs and proportionality. In this first graph, in the top left-hand corner, we have a directly proportional relationship. So why do we have a directly proportional relationship? Well, that's because firstly, we have a straight line. So we have a linear relationship, a straight line. And secondly, we have a y-intercept equal to 0. So if you like, where we have a straight line and a y-intercept equals 0, we're demonstrating a directly proportional relationship. So this would be like if we wrote Newton's law in the sense that we normally write it, which is F equals ma. The force is directly proportional to the acceleration. So this has the general form y equals mx. So that's a directly proportional relationship. And that's actually often what we want to aim to get in physics. We want to see what relationship gives a directly proportional relationship. The second relationship that we have down at the bottom here, bottom left, is a linear relationship. So we have a straight line, which is what makes it linear, but it is the y-intercept is not equal to 0, so it's equal to 1 here. So that is indicating that this isn't directly proportional. We're going to talk later on when we do the evaluation of pracs about what y-intercept's not equal to 0 means when we're looking for a direct proportionality relationship, it's usually a sign of systematic error. But we'll come back to that later on when we look at analysing and evaluating data. So a linear relationship, and we'll have some of these that we come across this year also in terms of physics concepts, like when we look at the photoelectric effect later on in the year, has the form y equals mx plus c. So c is our y-intercept and m is our slope. I probably should have pointed that out in the general form up here. That was the slope, not to be confused with m, the mass, and c is an indication of our y-intercept there. So that's a linear relationship. The next one we have, and I'm just going to change to a smaller pen size, is the inversely proportional to. So y equals 1 over x is the function here that I've plotted. So we can see we get that general shape. And I've just shown the positive quadrant here because that's normally what we're interested in physics. I haven't worried about the negatives on each axis. So that's what an inversely proportional relationship. Finally, we want to look at a proportional to the square of relationship. So y equals x squared. So what we see here is our typical quadratic type shape. So when x equals 1, y equals 1. 1 squared is 1. When x equals 2, y equals 4. 2 squared is 4. When x equals 3, y equals 9. 3 squared is 9. So this quadratic increasing at an increasing rate is another way we like to say this. Here we say the slope is increasing at a constant. Sorry, the slope is constant. The slope doesn't change. Here our slope is increasing. So our slope is getting steeper and steeper. So we have an increasing slope which gives us this typical quadratic shape that's typical of what we see when we have a proportional to the square of type relationship. So just finally, to relate that back to what I did on the last slide, we can see here, if I, say with a directly proportional relationship, if I double x, so if I go from 2 to 4, I will double y. Y will go from 2 to 4. If I triple x, if I go from 1 to 3, x will also triple, go from 1 to 3. Where I have an inverse square relationship, if I double x, I will halve y. So at x equals 1, y equals 1. At x equals 2, y equals a half. So when we double x, we get half of y. So that's how basically that behaviour of an inversely proportional relationship, which we showed by calculation on the previous slide. And finally, if we have a proportional to the square of relationship, if I double x, I get 4 times, so 2 squared. Double 2 times, 2 squared, 4-fold increase in y. If I triple x, 3-fold increase, I get a 3 squared, 9-fold increase in y. So hopefully you can, I find it easy to think of that just in terms of the formulas, but hopefully now that you can see in terms of directly proportional, inversely proportional, and proportional to the square of, how we can sort of interpret that proportionality or determine that proportionality from also looking at a graph, and that accords with the way that we explained that using the formulas as well.